In our next example, we're going to look at congruence modulo the ideal generated by x and y in C adjoin xy. You just notice that xy is all polynomial combinations of x and y, but our polynomials now are allowed two variables. So p of xy, q of xy in C adjoin xy. In particular, this ideal, this is an example of a non-principal ideal. So you do need both of the generators, and I leave that proof to you. But if you could get away with just like a single function, you would find that if you looked at linear terms, you would have a problem. So anyways, this is a non-principal ideal, so we do need both the generators, and that's a check I leave to you. Okay, so let's first try to understand what this ideal is. So a general two elements in not the ideal, but in the ring are going to look like, well, oops, I went for the wrong symbol there. Are going to look like, well, you're going to have a constant term, which I'm going to call A00, and then you're going to have an x term that I'm going to call A10, and then you're going to have a y term that I'm going to call A01, and then you might have a x squared term, which I'll call A20, at least the coefficient of it, and then you might have a mixed term, an xy, A11, and then you might have a y squared term, and so on. And then similarly, q of xy would have a constant, maybe a linear in x, maybe a linear in y, maybe a quadratic in x, and so on. Okay, so the subscript is a double index, and it tells you what it's a coefficient of. So A00, for example, is the coefficient of the x to the 0, y to the 0 term. A10 is the coefficient of the x to the 1, y to the 0 term, and so on. So this is a standard way of working with polynomials in more than one variable. All right, so what happens then if we take xp of xy plus yq of xy? Well, it's going to add, let me put maybe in orange, it's going to add an x to every term when we do this. I'm just going to add an x in. And then for the q of xy, that's also going to add a y into every term. So it'll be a y, that'll be an xy, that'll be a y squared, that'll be an x squared y, oops, and so on. So what happens when we add them together? Well, we're not going to get a constant term anymore. The new x term is going to be a00x, the new y term is b00y, and then we're going to get an a10x squared, and then the xy term is going to be a01 plus b10xy, and so on. I don't actually care what comes after that. But the point is that, well, we could pick our coefficients appropriately to get any polynomial without a constant term, right? You can always, if you have any polynomial without a constant term, you can rig it so that you can write it as a combination of xp of xy and yq of xy. So what we get here is that the ideal generated by x and y is precisely polynomials without a constant term. So this is very similar to the previous example we did, and it's a general fact. If you mod out by, if you have, say, n variables, you mod out by x1 through xn, you're going to get, again, polynomials without a constant term. All right, so what does it mean then to be congruent modulo xy? Well, let's do some examples now that we have an understanding of this ideal. So let's look at, for example, x plus y minus 2 and xy plus 2x minus 2. And let's look at their difference. All right, so let's see. Let me go to subtracting here. All right, minus 2 minus 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 2. sorry, the minus 2 minus minus 2, that's going to be 0. And then we're going to have a 2x and an x. So 2x minus x is x, and then we're going to have a negative y. And we can write this, if we wanted to, as x times y plus 1 plus y times negative 1, and that's certainly in the ideal generated by xy, because we would take p to be this guy and q to be that one. Okay, so that these guys, their difference is in this ideal, and notice the difference has no constant term. That's the criteria for being in the ideal, but we went ahead and we actually found explicit polynomial combinations of x and y to show we're there. So x plus y minus 2 is congruent to xy plus 2x minus 2 modulo the ideal generated by x and y. As an example. Great, let's do another example. Let's look, for example, at xy minus x minus y and x squared plus xy plus y squared. All right, and let's look at their difference. So x squared plus xy plus y squared minus xy minus x minus y. All right, what's going to cancel? I think the xy's cancel, and then that's it. So we're going to get x squared minus minus x is plus x, and then y squared minus minus y is plus y, which we could write as x times x plus 1 if we wanted, and y times y plus 1. In particular, that is a combination of the generators of our ideal, x and y. It's x plus 1 times x, and then y plus 1 times y. Also, notice the difference has no constant term. Cool. And here's just explicitly showing it's in the ideal. All right, let's do another example. Our last example, let's look at xy plus y plus 1, and let's look at 2xy plus 2x minus 3y plus 2. And let's look at their difference. So 2xy plus 2x minus 3y plus 2 minus xy plus y plus 1. All right, we have a 2xy and we have a minus xy, so that's going to give us an xy. We have a 2x that's not going to get subtracted off. We have a negative 3y minus y for a negative 4y, and we have a 2 minus 1 is plus 1. Ah, we have a constant term. So since we have a constant term, this is not going to be in the ideal generated by x and y, which is okay. I don't know why I'm using red for that. It's not like a bad thing by any means. It's just not in that ideal. So we learn from this that xy plus y plus 1 is not congruent to 2xy plus 2x minus 3y plus 2 modulo xy. It's not congruent to them because, well, you don't get the same thing. Or sorry, when you take the difference, you have a non-zero constant term, and that's all you need to do to check. You get this non-zero constant term, can't possibly be in there, and you can sit here and you can try to factor out an x and a y. And so, like, if you didn't believe that, maybe you're not too happy with that explanation, you could try to like factor out an x from the first guy, and then you could try to like factor out a y from what's left. But then you have this extra bit, this bit's extra, that you can't factor out an x or a y from. Okay, so you're not going to be able to express it as a linear combination of x and y.